Hello, 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 hello. Thank you. Wow, that was pretty accurate. I don't know if I need to say anything more, really. That's pretty much good. I'll just unlock that again. OK, so yeah, I am Peter Marshall, and I'm going to talk about life of a JavaScript feature in V8. A little bit about me. I've been working on the V8 team in Munich for 2 years now. I work on new features, and I also work on supporting V8 in terms of what embedders need. So Node.js, for example. I work a bit on the tooling. Specifically, I've worked on TypedArrays. I've worked on the spread operator. I've been working on the CPU profiler at the moment. So lots of different things, but basically focused on making V8 fast. What's V8? V8's the JavaScript engine, virtual machine. The same thing here, basically. And it's also in Node.js. So anytime you're running JavaScript, it's running in V8. More specifically, what that means is, oh, no, we're going to skip that part. Oh, here it is. Yeah, no, OK, good. How do features get into JavaScript is basically what we're going to be talking about. We're also going to be talking about how they're implemented and what they look like once they're in JavaScript, because you read the documentation on Mozilla and you see, OK, that's how it works. But what does it look like? We're going to implement a feature in V8 together, a new one that I invented. We're going to talk about a thing called V8 Talk, which is a cool new language we invented to write JavaScript features. And we're going to talk about the biggest challenges, which are compatibility, speed, and security. And we're going to talk about how that affects JavaScript developers, like how that's relevant to all of you today. So V8 on a high level works mostly like this. You have your JavaScript code, and it comes in. And then some magic happens, and there's a CPU involved, and then your numbers come out. But we're going to sort of demystify that a bit. So V8 is the magic box that eats the JavaScript and gives you the result, right? And inside of V8, there are more magic boxes. One of them is the ignition interpreter. And basically, when you give code to V8, it's going to run your code in this interpreter. It doesn't try to do any sort of optimization at this point. It just runs the code and gives you the result. So it's slow but predictable, and it can handle all of JavaScript. Once you've run that code a few times and we think, yeah, you really like this piece of code, it's hot now, we're going to try and make it faster. And we do that using the turbofan JIT compiler. And JIT means just in time. So while we're running your code in Ignition, we're secretly on the side compiling that code again using our just-in-time compiler. And we do that using type feedback that Ignition gives us. So JavaScript is a dynamically typed language. We don't know what types things have before you actually run the code. So once we know what types you have, we can generate faster code, and that's what we do here. So for our add function, for example, we're going to generate some machine code, and then we're going to run that on the CPU and give you the same result. So they do exactly the same thing, but they have really different strategies how they do it. And we put these two things together, and this hopefully makes your code as fast as possible. So JavaScript features. I would split JavaScript features into two camps, basically. But features start life as an idea. The first type of feature I want to talk about... No, we're talking about where JavaScript features come from, apparently. OK, so JavaScript features come from the ECMA committee, the TC39 committee, and they are the ones who write the language specification for JavaScript. There are 5 stages to the ECMA process. They are denial, anger, bargain. No, wait, that's not right. Hold on. It looks kind of like that, but it's actually slightly different. OK, so stage 0 is an idea. So if you have an idea for JavaScript, you're like, I really want this thing in the language, then congratulations, that's stage 0. Stage 1, you have to write some stuff on GitHub, and it sort of gets gradually more complicated from there. But the stage you probably care about is stage 3, which is where we actually implement that feature in Chrome and in V8 most of the time. And stage 4 means it's accepted into the specification, and this is sort of the language you know. So when we want to split features into 2 categories, which I like to do, then you have syntax and you have built-ins. So syntax is about changing the actual syntax of the language, adding new things that are valid JavaScript, right? And an example of this that I worked on is REST parameters and spread call syntax. So this is just a nice piece of syntactic sugar, I guess. You've probably seen this in what you're using every day, but you see you can just take all the parameters to this max with floor function and sort of group them up into this array. And then when you call math.max, you can use the spread operator, which is these 3 dots, and that just passes all the things in that array as parameters, because math.max accepts a variable number of arguments. So that's syntax, basically. With syntax, we have to be careful. So we can introduce new syntax, but we don't want to break old code that's still running. So we can't we can't remove syntax from the language generally. And web compatibility is taken really seriously, and this is the reason why. So for example, you might have heard of something earlier in the year called Smushgate, which is where we were trying to add a new language to a new feature to the JavaScript language. But it kind of went badly. And basically, we were trying to add a feature called flatten to the array prototype. It turns out that a bunch of websites were using a library called MooTools, and it already had a method on the array prototype called flatten, and it sort of conflicted with the one that these JavaScript spec people wanted to add, and it was going to turn out that we would break all of these websites if we added this feature. And the cool thing about the web is that all these old websites still work, like the Space Jam website from 1996 or something like that. So yeah, this caused a bit of controversy. So wait, what does this have to do with Smush? Well, somebody suggested that instead of calling it flatten, we call it Smush, because then the names won't collide, and some people got mad about that. Anyway, it's called flat now, and we've implemented it in V8. So the other thing that I actually want to talk about is JavaScript built-ins. And that's maybe not a term that you know. So built-ins, basically there's 912 of them in V8. And built-ins are everything you see that is like a provided object to you in JavaScript. So like the typed array, the array, all this kind of stuff. It's also all of the methods on the typed array. So if you look at things like filter, find, for each, sort, reduce, all of those things, each one of them is a built-in in V8. As well, it's not just typed arrays. We also have like everything on the string prototype, math random, array sort, and some internal V8 helpers too. So there are lots of built-ins, is my point. After we've had our idea and it's gone through the TC39 process, it goes into the specification. And it's useful looking at the specification. It's probably not a great way to learn the JavaScript language, but if you're looking at the VM level and you're implementing it, then this is what you follow every day. So I always have a tab open with the spec in it. So if we took this code, which creates a new uint array of size 8, then we could look in the specification for what this is actually meant to do. And we would see that, OK, there's a lot of words, but the top bit is the specification for the typed array constructor. And you see it takes a length as the first argument. And then it has 5 steps. And each of these steps also has substeps in that some of them are links, and you can follow those links. So step 5 is allocate a typed array. So then we click on that, and we follow this bit to allocate typed array. And you see it has some substeps as well. And you can start following them. And if you do that, then you'll end up reading about half of the specification. But you know, it goes on and on. So that's what it looks like. But what does it look like in terms of code? So first of all, when we get these new features, basically what we want to do is implement a baseline version that's really fast. That's not too fast, but it just covers everybody's use cases. Like it's specification compliant, it passes all of the tests. But the thing is, we don't know how people are going to use features yet. So with something like spread, we didn't know what types of things people are going to be spreading. Are they going to be calling it on arrays? You can also call it on a string because it just calls the iterator protocol. So we don't know how people are going to use features, which brings me to the first point, which is that we really need developer feedback from people who are using JavaScript or writing frameworks in JavaScript or whatever. Because we're not JavaScript developers. I really can't write JavaScript very well. People talk to me about JavaScript all the time. I'm like, I know what that is. So we need feedback from you, because you people actually know how to write JavaScript. But if we don't have this feedback, then we end up with this kind of situation where people write code that is fast but doesn't look very nice. They sort of hack around the language features. And you end up with comments like this that's like, yeah, this code is terrible, but it's really fast. Sorry it looks like this, but if I do it the proper way, then it doesn't look, it's really, really slow and unusable. So this leads me to a really nice quote, which Gandhi definitely never said. And it goes, be the change you want to see in the world. But I would change it slightly, and I would say, write the code you want to see in the world. And what this is about writing idiomatic JavaScript. So what you should be able to do is write the JavaScript you want to write. It should be expressive, self-documenting, all this kind of stuff. And then we should be making it fast for you. Like, that's the point of the implementations. OK, what does a built-in look like in V8? So V8 is mostly written in C++, I would say. And when you compile C++, you turn that into assembly code, and good. We also have some other languages we use in JavaScript, in V8 to implement JavaScript. We also have some self-hosted JavaScript. So part of the JavaScript engine is written in JavaScript, and we compile it with itself. It sounds really cool, but it turns out this is a bad idea. And so we generally don't do this anymore. But I'll get into that. We also have this thing called code stub assembler. And this is sort of like a language. But basically, it's sort of a high-level assembly language. So you can write code once, and then it generates assembly code for each of the, I think, 7 architectures we currently support. But that wasn't enough, so we invented another language on top of that called V8 Talk, which is pretty cool, and I'm going to talk about Talk today. Each of these languages has different trade-offs. So we also implement stuff just raw in assembly code sometimes, but when we do that, we have to implement it for every single architecture we support, which is, I think, 7. So it's kind of this trade-off between performance, developer ergonomics, and safety. So how fast it is, how easy it is to use, and sort of how hard it is to shoot yourself in the foot with it. Assembly code, it's really, really fast. That's about all it has going for it, essentially. Like, it's terrible because you have to write it 7 times, and it's really unsafe. It'll let you do whatever you want. But we still need to use some of this, so we do that. Code stub assembler is sort of a step up from this. It's a bit nicer, but it'll generate all that assembly code for you. And then hopefully Talk is kind of the solution to this. We're trying to find this sweet spot. C++ is nice too, not necessarily as fast, not because it's a slow language, but just because of other things, which I'll get into. And JavaScript is like totally unpredictable. So this is why we don't like implementing things in JavaScript, essentially. I mean, I'm talking about self-hosted JavaScript here, not like JavaScript in general. So it can be really fast, or it can be terribly slow. It can do really surprising things, like we'll see, or it can be your best friend. So that's why we introduced this new language called V8 Talk. And Talk is about it's basically a custom domain-specific language for writing JavaScript built-ins in V8. So if you're thinking, how can I use Talk? Well, you have to contribute to V8 to do that. But that's all right. You can do that. It's open source. So it basically looks kind of like TypeScript. It has a TypeScripty syntax, except instead of JavaScript types, it's like the V8 internal types for those JavaScript objects. So that's cool because it works with linting and formatting tools that we already use. It's strongly typed with compile time errors, so this is another problem with implementing JavaScript in JavaScript. You don't know what happens until you run it. And this is kind of going to become the de facto language for implementing built-ins in V8. So we're sort of porting all the JavaScript code we have to that, self-hosted JavaScript code. And we're going to write all new things in that as well. So isn't it just the same thing as JavaScript, but with types? Well, no. It's actually a very different language. So it basically shares none of the semantics with JavaScript. And because this is our language that we wrote, it's sort of we control the semantics of it as well. So the syntax is similar, but they do very different things. So here's a code example of hello world in Talk. So the first 3 lines are the Talk. And then remember I said that we turn Talk into code stub assembler. So this is the generated code that we would create. So it makes pretty much sense already, I think. JavaScript built-in. It's called main, and then we pass in a context. That's sort of just like a variable environment. You don't really need to know what that is. And then we print hello world. Obviously, we generate a whole heap of boilerplate here to do that in code stub assembler. So if we actually wrote that code stub assembler ourselves, it would be a bit shorter. But yeah, you get the gist of it. We don't actually sit around writing hello worlds all day in V8. Generally, we do different things, like implement the JavaScript spec. So this is an implementation of splice, array splice, in Talk. And as you can see, it kind of looks like TypeScript. That's nice. And another really cool thing is that you see the green comments here are the actual lines from the specification that I showed you earlier. So you can see that it really closely follows the specification, and we can be sure that we're actually doing what the specification says because we're sort of operating at the same level as the spec. And so we do this, and this is sort of like our regular path. And then if we want to make something super fast by doing some cool tricks, we do that on a fast path. But we have this implementation to fall back to where we can see, yeah, it follows the spec. We have some really cool features in this, like we have operator overloading on like the less than and the plus, and we have all these helpers to do cool things for us. You see that the arguments come in, and it's like a REST arguments, like we were looking at before, and then you can just pull them out of the arguments with the square bracket thing. So this is really nice syntax. It's really cool to actually write code like this to implement JavaScript. So as I said, talk compiles to code stub assembler. I didn't get around to making a better picture for this, but basically we have all our talk files, which are .tq, and then we turn them into code stub assembler files using talk, and then we turn that into assembly code using code stub assembler. So I want to implement a JavaScript feature with you here today. We don't really need this feature, but it's just, we should implement something. So typed array prototype clear is one I want to suggest. And what this is going to do is it's going to take a typed array, and it's going to set everything in the typed array to 0. You can already do this by just calling .fill 0. Yeah, it's the same thing. But let's implement it in JavaScript, C++, talk, and code stub assembler, and then we can sort of compare the performance, and you can also see, OK, that was really nice, or that was kind of painful. Yeah, we wouldn't actually implement anything in self-hosted JavaScript anymore, but we'll just compare it. To do this, you just need to know about how typed arrays look in memory in V8, and it's useful to know that we have this idea of the raw backing store memory for a typed array. So for a typed array, so for a uint8 array, for example, it would look something like this. You just literally have the uints8 in memory next to each other. And you have a backing store pointer, which points to the first one. Yeah, that's pretty much it. So the self-hosted JavaScript would look something like this. We're just adding a method called clear to the typed array prototype. We have to call this thing called validate typed array. And this is sort of a spec level operation. You don't really need to worry about it, but basically the spec says we have to do that, so we did. The next thing we want to do is get the length of this typed array. So remember, what we're trying to do is just set everything in the typed array to 0. So we're going to take the length. You notice we have this weird percentage sign function thing going on. This is something we have to do in V8. It's called an intrinsic function, I think. We can't just call .length on the array because that can have side effects, which we'll see later can lead to security problems. So then we just take this array and we index into it and we set everything to 0. So this just looks a lot like a polyfill. Like if you were to write this feature in JavaScript and ship it as a library, then that's what it would look like, except for you would just call .length on it. The C++ implementation, we're going to do something slightly different. But it's basically the same thing. So you can see we're calling validate here on the bottom line. We have this handle scope thing. That's for our garbage collector. We're taking the length again, but this time we're taking the raw pointer to the backing store. So we're actually just going to get the data pointer out, so we have a pointer to the actual memory location. And then this is the cool part, which we can do with C++, which we couldn't do in JavaScript, which is we can just call memset on the backing store. And memset just takes that pointer and fills it with zeros up to the length that we specified. So this is a cool little optimization. I would say the C++ is kind of harder to read. Like, there's a lot going on here which is not important from an algorithmic point of view. It's just procedural. Like, yeah, you have to cast this thing. You have to get the elements. You have to get the data pointer. The next we'll look at is the talk implementation. So this is my favorite one. You can see we're just getting the typed array from the receiver object, which is this value of the function, basically. And then we're going to do the same thing to get the length out of this. So we get the byte length. No, we're in code stub assembler now. So we do the same thing to get the byte length out of it, but we're using a try catch block this time. And then we call memset on it, the same thing we did in C++. So these are essentially going to do the same thing, but yeah, we'll see what that looks like performance-wise. So the next one will be the code stub assembler implementation. So this is what the talk would generate, because remember, talk generates code stub assembler. And we're doing the same thing. We're going to validate the typed array. We're going to get the byte length. We're going to load the data pointer. And then we're going to call memset on this thing. Memset looks much worse here because we have to pass all the types in. But essentially, it's the same algorithm, right? So we're going to run this through a benchmark. This is a really terrible benchmark. Basically, it just creates a typed array, and then it calls on it 50 million times clear. There's no point in doing that, obviously, because the typed array starts filled with zeros anyway. But trust me, we don't optimize this out. JavaScript makes it so you can't actually do that. So the benchmark's not particularly meaningful, but it will test our implementation. So I ran all of these against each other, and the results are a little bit surprising. So the self-type of JavaScript is slower, so this is execution time on the axis. That's not that surprising because we didn't use this memset trick. We iterated through each element and set it to 0 individually. The C++, talk, and CSA are kind of close, but the C++ is actually quite a lot slower, which is surprising. The talk and the CSA are very similar. I mean, talk generates CSA, so it should be theoretically exactly the same. Because talk is new, I think we can probably improve the way it generates code stub assembler, so I'm not too worried about that. But the C++ is kind of strange that it's slower. And it's not because C++ is a slower language or anything like that. It's just because of this way we organize things in JavaScript, in V8 rather. So every time we transition between the JavaScript world and the C++ world, we have to go through this thing called the C entry stub. And this is basically to do with like the stack frame layout that we use in JavaScript is different to the one we have to use in C++. So we have to do all this massaging and run a few hundred instructions every time we go from JavaScript to C++, and the same on the way back. And we do this for every call to .clear. So remember in that benchmark, we were calling it 50 million times. Well, that's running in JavaScript land until we call clear, and then we jump to C++ land. So we pay this cost for every time we call clear, basically. So this sort of amplifies the effect. So I talked about various different things. So I talked about making it fast, but we also have to worry about making it secure. So as well as being compatible and fast, how do we make it secure? So JavaScript is kind of a strange thing in this regard. Like, in general, if a stranger sends you code on the internet, you shouldn't run that code on your computer. But this is exactly what the web is. Strangers send you code, and then you run it in JavaScript, right? And this is because JavaScript provides this safe abstraction level over the CPU, and it says, this is the virtual machine you're programming. You're programming a JavaScript machine. And your browser also has sandboxes and other defenses in case you happen to get out of JavaScript land. It turns out, historically, typed arrays are a really nice attack vector in V8. So yeah, we got hacked a lot of times just from typed arrays, which is why we're moving away from this JavaScript implementation. So again, we have this raw memory view, and we have these bytes just in memory, right? We have this backing store, and we have the byte length. And if we mess up this calculation somehow, then we're going to end up not in our typed array, but in the memory next to the typed array. And that's out of bounds memory, so that could contain other objects. So in the best case, maybe it's just the next typed array. But maybe it's some of these compiled code. Maybe it's your password, your credit card number. Yeah, this would be really bad. So the classic typed array exploit, and I'll put the slides up. You can follow the link to the bug. So this was put through a bug bounty program. And basically, you create an array buffer of size 8. This looks really nice. It's fine so far. And then you define a getter on the byte length of the array buffer. And what this will do is when you call arraybuffer.bytelength, this will return this really big value instead of our actual byte length. So we created an array buffer that lies about how long it is. And this should be fine. But it turns out it wasn't in V8. So we would call, so then you call the typed array constructor with that thing. And the typed array constructor has to be really clever about this and figure out that, OK, I can't just call byte length on that thing and then create an array that long because it's lying about its byte length. So we have to look at the actual byte length and totally ignore the value returned by this getter. If you don't do that properly, then you can just like read in and around this memory. So this will let you read up until this fake byte length that it gives you, but the array is only the real byte length, which is 8. So you have this massive out-of-memory area where you can actually read using JavaScript. So a lot of past exploits look like this, and pretty much all browsers, all the browsers have had exploits like this. But we find and fix these really fast. This is why we couldn't use the .length value when we implemented clear in JavaScript, because that could have a getter on it, or could be a proxy or something like that. So JavaScript tends to have these really surprising side effects, and that's why we can't use it to implement JavaScript, basically. So lessons for us are the V8 talk DSL. Yeah, we really like it. So normally when people tell me they fixed their problem with a domain-specific language, they have 2 problems now, right? But for us, it worked really well. And we have compiler people on our team, so they love inventing languages and writing compilers for them, so that keeps them happy. Implementing JavaScript in JavaScript is generally not a great idea. We had a lot of problems with it. We also had performance problems with it, and we're sort of moving away from that now. Security is really hard, so human beings are really bad at looking at a piece of code and saying, like, does this have this vulnerability that we talked about? And languages like V8 Talk can hopefully help us with this. So the long-term plan is keep working on Talk, and we can actually build things into the language, because we control that language, that will help us do these security things automatically. The takeaways for you, hopefully we remove a little bit of the magic, so maybe it's a little bit intimidating to think about something like working on a VM, but actually that JavaScript snippet I showed you, that is the only code you need to add to V8 to add a feature to it. You might need to add something in one or two other places just to register the fact that you put this new built-in here, and here's what it's called. But that's about it. So working on built-ins is a really cool way to start hacking around with the VM. You can add your own features that you always wanted. Yeah. Our challenges are about web compatibility, speed, and security. So you see how we sort of trade these things off as we decide how to implement things. We have different language options, but we have to think about, what's going to happen with speed, what's going to happen with security. Really, write the code you want to see in the world. So we have a lot of choices in terms of how we implement things, and we just want to make it as fast as possible. And the best way to push forward the JavaScript language is for people to write the code that they want, and for VMs to work on optimizing that and making it fast. So send us performance feedback. You can hit me up on Twitter. I'm HoorayBuffer. You can put something on our issue tracker. You can hit up V8.js on Twitter, but make sure you get V8.js and not V8, because they are vegetable juice. And they're really sick of hearing about JavaScript issues, and we're really sick of hearing about vegetable juice issues. So get that one right, yeah. OK, thank you very much.